Now let's focus on these organic rich source rocks. As you've seen this slide before, and it's basically showing the distribution of these source rocks. But another way to think about this is that everywhere hydrocarbons have ever been produced, there are source rocks. And traditionally, we searched for and produced from reservoirs representing hydrocarbons that migrated out of the source rocks and into those reservoirs. And now we have the potential to go into those source rocks themselves. So one way to think about the distribution of organic rich source rocks that could be a target for unconventional development is that everywhere hydrocarbons have ever been produced is now a place where we can consider the source rocks that produce those hydrocarbons as possible targets for future development. When we talk about carbon, we have to recognize that it comes in various forms, and the image on the right, the image on the left shows that by volume, by volume or mass, we're normally going to represent TOC by mass content, but it's very small. By mass, it's typically a few percent, maybe 1 or 2%, maybe as much as 7%, but usually somewhere in between. Now, the carbon, which starts as organic matter, which turns into kerogen, sort of a waxy organic substance, then with increased temperature and to a degree pressure, but mostly temperature, it matures, producing gas and oil. And as a function of maturation, or as a function of temperature, first and foremost, what you see is the amount of oil increases. We'll see that as more quantitatively in the next slide. Initially, and then the ratio of gas to oil increases, and finally you can over mature a organic bearing source rock and just result in dead carbon, in which all the volatiles have been converted and burned up basically, and are no longer available for production. This slide from Peters et al. Summarizes all of this rather nicely. What's basically being shown as a function of depth is depth and temperature, of course, trade off. A typical thermal gradient in many of the areas we're interested in is 25 to 30 degrees C per kilometer, plus the mean annual surface temperature, which might be something like 10 degrees centigrade. So we start seeing significant crude oil accumulations starting at about 60 degrees, peaking at around 90, 100 degrees, and between 100 and 200 degrees, we go through an oil to wet gas to dry gas transition. And beyond temperatures of more like 250, we're, everything's burned up and we're left with dead carbon. We'll see that in the next slide as well. We use the reflected light amplitude from vitrinite as a metric for maturation, and it goes by the R sub 0. And when it's about 0.91%, we're sort of near peak oil. And when we're at around 2.0, we're in completely dry gas. And when we're at higher levels of maturity, we're outside the gas window. Most of the gas we're interested in is thermogenic gas produced in the manner described, the maturation of kerogen. Although at relatively shallow depth, you get biogenic gas, especially in areas where coal is present. Coal bed methane, or coal seam gas, as it's known in Australia, occurs at shallow depth in which bacteria in groundwater digest the coal and produce the methane, which then winds up being a combination of adsorbed gas on the coal surfaces and some free gas. This table summarizes things pretty well. The vitrinite reflectance is in the middle. Carbon content on the left. We're not so interested in the grades of coal. Different types of kerogen are indicated on the right, and depending on what type of kerogen it is, you would tend to get a predominance of gas over oil at a given range of temperatures. So basically, what you're seeing is temperature go up, the kerogen being converted to hydrocarbon, or eventually over-matured, all burned up. What is happening diagenetically is shown by the petrology stages in a very generalized sort of way. But it's a nice overview of how vitrinite reflectance, temperature, and maturation and production of hydrocarbons occurs with depth, and if you and temperature, and if you wanted to again assign specific depths to this, again keep in mind a reasonable thermal gradient is 25-30 degrees per centigrade per kilometer. When you look at maturation and production, you see good correlations in many places. In the Fort Worth Basin, for example, where in the map on the left, the oil wells are shown in green and the gas wells in red. So the gas was the big unconventional play that started around 2005. The maturation, as you can see in the middle diagram, basically matches all of this. Maturation is the vitrinite reflectance is over 1. The hydrogen index is low, as would be expected in the gas window, and the kerogen transformation ratio is actually pretty high in that same area. So the occurrence of gas in this part of the basin is consistent with different indicators suggesting that there should be gas there based on how we interpret these various metrics. And that's all I really want to say about maturation at this point. Different kinds of kerogen, which are at different but similar temperatures, and we go through this oil, gas and oil, dry gas transition as we go through increasing temperatures in the areas of interest.